Hi guys, today we're going to start our introduction on acids and bases. We'll talk a little bit about the different definitions of acids and bases, their properties, and a little bit about how they interact with each other. Let's get started.
All right, so this is the first lesson in your acids and bases unit, and it's pretty heavy on vocabulary, so I've put some stars by the really important vocabulary words. That's as opposed to some of our later lessons that will be more calculations based. So to start off, you probably have heard of acids and bases before, probably heard a lot about them. Basically, they're two categories of chemicals that have some special properties. They do react with each other in a very certain way, and something to keep in mind is they're not necessarily exact opposites of each other. A lot of people think that because acids will burn you and we hear that they're dangerous, then bases must be the opposite. They must be harmless. Well, that's not really true. As you can see in the pictures here, Drano is an example of a base, and obviously that's not harmless. So there's a wide spectrum of acids and bases that we'll talk about. All right, so what is an acid? An acid is a substance that dissociates or ionizes in solution. That means that it breaks apart in solution to form hydrogen ions. This is by far the most important thing that we need to remember that acids do. Acids somehow produce hydrogen ions in water. So a really simple example, an acid that we're familiar with at this point in the year is hydrochloric acid. When we dissolve it into water, it actually splits apart into hydrogen and chloride. So the fact that it produces this hydrogen ion makes it an acid. Now, the hydrogen ion by itself is actually not stable, and it will latch on to water molecules and form this hydronium ion. Okay, so what happens really is when the hydrogen chloride or hydrochloric acid breaks apart, the hydrogen actually latches onto a nearby water molecule, and it forms this ion, which can be written as H3O+, and it's called hydronium, and then the chloride is left all on its own. Okay, so you can say that acids produce hydrogen, or you can say that acids produce hydronium, and you're kind of saying the same thing. They really mean the same thing, because if you say hydrogen, you're really implying that it forms that hydronium H3O+. But the main idea is that either one of those indicates that you have an acid on your hands, okay? Hopefully not literally. All right, the presence of these ions are what give them their acidic properties. So what are those properties for acids? First off, they taste sour. So things like lemon juice, citric acid, things like that, they taste sour. They produce hydrogen gas when they react with metals, and that's a single replacement reaction. So a real quick example of that would be zinc and hydrochloric acid. It would be a single replacement reaction. The zinc would kick out the hydrogen, so hydrogen gas is released, and then zinc chloride is left behind. Okay, so an acid with a metal is going to produce hydrogen gas, and let's think about what they do with different substances. They react with carbonates to form carbon dioxide and water. So another example, and we did a lab on this earlier in the year, if we put sodium carbonate together with an acid, this is a double replacement reaction. So the hydrogen and the sodium swap places, so we get NaCl, which is kind of no big deal, salt. But then the other substance that we get, I'm going to write it off to the side, when you get hydrogen with carbonate, you get H2CO3. But we've learned that that decomposes upon formation, so we don't write it. It forms water and carbon dioxide gas. So when an acid reacts with a carbonate compound, it produces carbon dioxide gas. So acids with different chemicals can produce some gases. Other properties, they turn litmus paper red. We'll talk more about indicators later in the unit, but basically you might have heard of a litmus test. A litmus test on acids and bases results in a red color if you're testing an acid, and we'll see that it forms a blue color in a base. Finally, they are electrolytes. That means they'll conduct electricity when there's a solution, and the reasoning behind that is when an acid dissolves in water, you get this charged particle, the anion, left over, and you get this charged particle over here, the hydronium, and so you have charged particles floating around in solution, and that's what makes an electrolyte, mobile charged particles that can conduct electricity. All right, how much do they conduct? That depends on what kind of acid it is. So we actually have strong acids and weak acids. So by definition, a strong acid dissociates completely, okay? 100% dissociated. So for instance, if you put 1 mole of hydrochloric acid into some water, you're going to get 1 mole of hydrogen ions. Or if we look back to this problem here, if we think about it in terms of mole values, if we dissolve 1 mole of this, it's going to produce 1 mole of leftover chlorides and 1 mole of the hydronium. Okay, so 100% of the hydrogen chloride or hydrochloric molecules break apart. So if you started with 75 molecules, you'd get 75 chlorides and 75 hydroniums. By definition, that is a strong acid. Now, weak acids, on the other hand, only dissociate a little bit, and what that means is maybe about 5% of the molecules will actually break apart, okay? So if we have a beaker of a whole bunch of acetic acid molecules, and for acetic acid, I'm going to abbreviate that as just HA, so A is the acetate. If we have 100 HA molecules, okay, maybe only about 5% of them are actually going to turn into ions. The other 95% are going to stay as is. They're going to stay together as HA molecules. So we get very few ions produced, so they're actually weak electrolytes. They do conduct electricity, but just not quite as much, okay? Because they don't dissociate completely when we write the reaction, we typically write it as a double arrow, whereas when we did a strong acid, we wrote it as a single arrow to indicate that, yeah, all this stuff completely changes into that product, versus a weak acid that does not, okay? You do need to know some basics about your acids. You definitely need to know which ones are strong. If it's not on the list of strong acids, it's a weak acid, okay? There's only 7 strong acids. So HCl, H2SO4, and HNO3, these are our first 3 strong acids, okay? HCl, by far, the one that we see most commonly in our chemistry labs. We just deal with it a lot. Sulfuric acid, we did a demo with that and sugar, and we saw the big black carbon tower form. Nitric acid we don't deal with a lot. It forms a lot of bad gases sometimes. Other strong acids to know: perchloric acid, HI, hydriodic acid, and HBr. And actually, there is one additional strong acid that you might want to add to your list, HClO3, which is just chloric. Okay, so again, there are only 7 strong acids. Anything else is a weak acid. So all of these 7 strong acids here dissociate 100%. Our weak acids, these are just some common ones. Phosphoric acid, H3PO3. So even though it has 3 hydrogens, it doesn't really give them up very easily. It does tend to stay together as H3PO4, so we don't consider it strong. Sometimes you can see that ingredient listed phosphoric acid on sodas. One that's definitely found in sodas is carbonic acid, H2CO3, and that's carbonic acid. And then this is acetic acid. This is one way to write it. There's your hydrogen, and this is the acetate, okay? The other way that we write it is HC2H3O2. And again, there's your hydrogen ion, and there's your acetate, okay? This is the main component of vinegar. So it's very common. All right, another vocabulary word, this should have a star by it, a polyprotic acid. We've seen some polyprotic acids in our list. A polyprotic acid is an acid that has more than one ionizable hydrogen. That basically just means it has more than one hydrogen in it. So like H3PO4 we saw a minute ago. In theory, it could lose 3 hydrogens, so we call it polyprotic, okay? We need to talk about why we call that protic, not polyhydrogen or something like that. Why do we call it a proton? But the thing to remember about it is that the hydrogens break off one at a time. So another example of a polyprotic is sulfuric, okay? So because it has 2 hydrogens, 2 reactions are actually happening, one and then the other. The first reaction, it loses 1 hydrogen and it forms HSO4. And then that HSO4 loses its hydrogen and finally becomes sulfate with no hydrogens left over, okay? So this happens first, and then this happens second, okay? We have to lose 1 hydrogen before we can lose the second, okay? Let's go back and let's talk a little bit about why we call it polyprotic, okay? We said that acids are substances that ionize to produce hydrogen ions. Let's talk a little bit about what a hydrogen ion is. Okay, so I'm going to go to a blank screen real quick. If we think about a hydrogen, just a plain old hydrogen atom, and what it's made of, it's one proton, one electron, and 0 neutrons. Okay? When we talk about the hydrogen, positive hydrogen ion, well, in order for it to become positive, it has to lose its electron. So what's it made of? One proton, 0 electrons, and 0 neutrons. Okay? So I should have mentioned this earlier, but we actually have 3 synonyms for what acids produce. We could say that acids produce hydrogen ions. We could say that acids produce hydronium ions, because again, when it latches onto water, that's what it forms. But we could also say that this is the same thing as a proton, okay? So acids are hydrogen producers, acids are hydronium producers, acids are proton producers. All of these things mean the same thing. Okay, so let's move on and let's talk about bases a little bit. Bases are substances that react in water to form hydroxide ions. So acids produce hydrogen, bases produce hydroxide. This is just a key definition of what acids and bases are. The presence of that hydroxide is what gives bases their basic or alkaline properties. Okay, alkaline is another word for basic. Okay, the OH can come from the molecule itself. So you might have NaOH, which very obviously is going to have hydroxide in it. Or it could come from an interaction with water, which we're going to look at in just a second. So, what are the properties of bases? They taste bitter, and they feel slippery. So, think about soap. Okay, key ingredients of soap are bases. They turn litmus paper blue. So again, there's that litmus test. Acids turn it red, bases turn it blue. They are electrolytes in solution. That means that they produce ions. Okay, and I just like to point it out, they can damage your tissues, okay, like burn your skin. Again, a lot of people think, oh, acids are going to burn me, so bases must be fine. No, bases can actually cause more damage sometimes. So here's different ways that we can get hydroxide. This first one, it's pretty darn obvious that this has hydroxide in it, so when it ionizes or breaks apart, it's going to form sodium and hydroxide, and there's that hydroxide that makes it a base, okay? NH3 is also a base, okay? When it interacts with water, NH3 is actually like a hydrogen thief, and it takes a hydrogen away from the water. So if we take one of these hydrogens from water and give it to NH3, that becomes NH4+. So the NH3 turned into NH4+, and the water lost a hydrogen. It was stolen from it, so it leaves behind OH. Well, there's your OH. That's what makes it a base, okay? Hydrogen carbonate kind of does the same thing. It's a hydrogen thief, and it takes it from the water. So the hydrogen carbonate is a hydrogen thief. It becomes H2CO3. The water lost its hydrogen to the thief, and it became OH-. So again, there's that OH that makes it act like a base. All right, you do need to, again, know your bases. The strong bases are the hydroxide compounds of group 1 metals, so we don't include hydrogen because it's not a metal, and the hydroxides of group 2 metals except for the top 2, okay? So group 1 metals, these are just a couple of examples. It might be NaOH, KOH, LiOH, those are your group 1 hydroxides. And then our group 2 hydroxides, same thing. So calcium hydroxide, strontium hydroxide, and I'm just going to say etc. The only ones out of group 1 and 2 that we don't include are hydrogen, and then the top 2 from group 2. So the first one in group 1 and the first 2 in group 2, we don't include those, but any other group 1 or 2 element with a hydroxide is a strong base. Pretty much any other base is a weak base. NH3 is a good example. Okay, baking soda is a good example. It's specifically the hydrogen carbonate ion, not the sodium, that is the base. Okay, what you want to look for bases are compounds that have nitrogen in them, so like NH3, or negative ions. Those tend to form bases, and we'll talk about why that is in a minute. The strength is again determined by the degree of dissociation. These dissociate or ionize 100%. They form a whole bunch of ions, and these only ionize about like 5%, so it's not producing a lot of ions. All right, a neutralization reaction is a reaction between an acid and a base, okay? In general, it's going to produce neutral, as in non-acidic or non-basic products, okay? The simple kind of generic equation that you can remember is that acids plus bases produce water and a salt. So let's look at an example of that. Here's our acid, HCl. Here's our base, KOH. And a lot of times these just look like double replacement reactions. The simplest way to think of this is the hydrogen and the potassium are swapping places, okay? So the hydrogen and the potassium swap. So hydrogen is no longer with chloride, hydrogen is with hydroxide, so that forms the water. And then potassium pairs up with chloride, so this is the salt or the ionic compound. And neither one of these is significantly acidic or alkaline, so we've gone from an acid and a base with very unique properties to mostly neutral substances. Okay, so we can do a little bit of practice with this. Let's just do one. Let's do phosphoric and potassium hydroxide. So I'm going to go to a blank screen for this, phosphoric and potassium hydroxide. So H3PO4 and KOH. Again, just think of these as double replacement. So the hydrogen and the potassium are going to swap. So the potassium is now going to be with the phosphate. So when you do the crisscross ion charges, it's K3PO4. And hydrogen is now going to be with hydroxide. And if you think about hydrogen hydroxide, that's water. So H2O. And of course, we have to balance it. I see that potassium is not balanced. I always start with my metals, so I need 3. So I'm going to put a 3 over here. And then I have 3 hydrogens and 3 hydroxides, so I'm going to make 3 waters. So that would be my final balanced neutralization or acid-base reaction. Okay, now we get into the different definitions of acids and bases. These kind of go in chronological order of when they were figured out. In addition to that, they also kind of go in order of complexity of the definition or sophistication of the definition. So this first definition is really simple, okay? This is called the Arrhenius Definition, named after the scientist who kind of figured it out. Arrhenius acids contain hydrogen, H+. Arrhenius bases contain hydroxide, OH-. And that's pretty straightforward. That's kind of the definition we already talked about. If something ends up producing a hydrogen, it's an acid. If it produces a hydroxide, it's a base, okay? But the key word here is contains, okay? So the formula itself actually has to contain that ion. So the acid has to have the hydrogen in it. That's usually not a problem, but the base has to have hydroxide in the formula. Now, this does not explain why substances like baking soda and ammonia, which again, if we think of their formulas, NH3 or the bicarbonate ion, which is in baking soda, these are bases. They produce hydroxide. They have all those basic properties. So the Arrhenius definition doesn't include them, so we need to expand on it. So this truly is the most simple definition, but it's not all-inclusive. It's not good. We need to be more inclusive. So this is where the Bronsted-Lowry definition comes in, and this is what we're really going to focus on in pre-AP chemistry is this Bronsted-Lowry definition. So the Bronsted-Lowry definition of an acid is any substance that can donate a hydrogen ion, which we talked about earlier is really called a proton. So we call Bronsted-Lowry acids proton donors, okay? They give away hydrogens or give away protons. So you got to remember, again, H+ and proton, that's a synonym. Those mean the same thing, okay? So if it has a hydrogen in it and it can give it away, it's donating it, it's an acid, okay? I want you to think of this kind of like a game of catch. This is the pitcher. He's throwing the hydrogen ion away. He's giving it away, okay? Then we have the Bronsted-Lowry bases, any substance that can accept the hydrogen ion. So this is kind of like the catcher. So he's catching the hydrogen ion. Now, if you think about it in relation to water, if water is the pitcher and this bicarbonate ion is catching from the water, okay, OH is produced, okay? Because again, the water lost a hydrogen. Same thing with ammonia, okay? Ammonia is going to take a proton from water. So when it took a proton from water, it left behind hydroxide. So again, that OH right there It wasn't in the formula. Neither one of these had hydroxide in the formula. But through their interaction with water, taking a hydrogen from water, they actually can form that hydroxide ion. This is, again, the definition we're going to use most often. So let's think about this. Which of the following bases are an Arrhenius base? So I'm telling you that both of these are bases, but which one is Arrhenius? Arrhenius was the simple definition. It has to actually have hydroxide in the formula. So the answer is this rubidium hydroxide. This is an Arrhenius base, okay? Fluoride is also a base, but not according to the Arrhenius definition. It's a base according to the Bronsted-Lowry definition, okay? And again, all that means is that it can take on a hydrogen. Well, why can it take a hydrogen? Because it's negative. If you think about water giving up its positive hydrogen ion, again, water is really made up of a hydrogen and a hydroxide. That hydrogen can be lost, and it's going to be very strongly attracted to this negative fluoride. So that's going to form HF, and then what was left over from the water, just hydroxide. So again, it's a base because it made hydroxide. All right. Finally, the third definition is the Lewis acid and base. I'll be honest that we don't do much with this in pre-AP chemistry, but we can talk about it, okay? Lewis acids are electron pair acceptors, so they're usually positive. They're lacking an electron pair. They have an empty space for an electron pair, and bases are electron pair donors, okay? Electron pair donors means that it might have some like bonds to some stuff, okay? But it might have this lone pair of electrons out there, okay? So the definition that I want you to know is this NH3 and BF3, and we really need to draw a picture of it to understand which is which. So if we think about NH3, the Lewis structure looks like this, and then BH3, or BF3, I think we had, looks like this, okay? Basically, boron doesn't have its full octet yet. It's got this little empty space right here, okay? So the ammonia can donate that electron pair and share it and bond onto the boron trifluoride, and so it's going to make a combined molecule. So I'm going to rotate the the ammonia a little bit. There's that new bond, and it's going to bond onto the BF3, okay? So this donated an electron pair, so it was a base. This accepted an electron pair, so it was the acid. That's about all you need to know in pre-AP chemistry for that. Okay. Our last little topic here is something called a conjugate acid or base, okay? Basically, when we have an acid-base reaction, it usually can be reversed, okay? So we consider it in the forward and the reverse reaction. So if we consider hydrogen, HX, whatever that might be, turning into X minus, HX lost a hydrogen, so it would be classified as an acid, okay? But if we want to consider the reverse reaction, let's consider the reverse reaction. X turning into HX. In the reverse reaction, X is accepting a hydrogen. Well, who accepts hydrogens? Bases do. So in the reverse reaction, X is acting like a base, okay? So the main idea is if we're talking about the reverse reaction, it's also an acid-base reaction, but we just call them conjugates instead, okay? So X would be the conjugate base because that means it's a base in the reverse reaction, okay? If we consider the water, kind of does the same thing. In one direction, we have an acid losing a hydrogen. In one direction, we have a base gaining a hydrogen. So in that direction there, it's gaining a hydrogen. Who gains hydrogens? Bases. In the reverse reaction, we're losing a hydrogen. Who loses hydrogens? Acids do. So in the reverse reaction, the thing that we started with, we would call that a conjugate acid. Okay. You might want to write down the phrase, and I'm going to write this out for you. You might want to write down the phrase, the acid becomes the conjugate base. I'm going to abbreviate that CB. Okay. The acid becomes the conjugate base, and then the base becomes the conjugate acid. Okay. Now, how do they do this? The acid becomes the conjugate base. What do acids do? They lose a hydrogen. So the acid becomes the conjugate base by losing a hydrogen ion. The base becomes the conjugate acid by gaining that hydrogen ion. Okay, so feel free to pause that and write that down before you move on. So let's look at an example. In this example here, we're going to basically label acid, base, conjugate, base. So let's just kind of look at the pairs here. NH3 is clearly turning into NH4+, okay? Well, how is it doing that? NH3 becomes NH4+ by gaining a hydrogen. And we ask ourselves, who gains hydrogens? Bases do. So this is the base, and the base turns into the conjugate acid, okay? Now look at water. Water turns into hydroxide by losing a hydrogen. Who loses hydrogens? Acids do. So water was actually acting like an acid, and the acid turns into the conjugate base. Let's do one more. Okay. Actually, we don't have another example. But in this example, notice that water was acting like the acid. Okay. In other examples, and I'll jot one down right here at the top real quick. In other examples where hydrogen gives away its, hydrochloric acid gives away its hydrogen to water, it forms Cl and then that H3O+. The water is turning into H3O+ by gaining. It's acting like a base. Okay, so we see that water can act like an acid or a base, and this is just another vocab word, amphoteric. If you think about other words like amphibian, which means, water or land, amphoteric implies that it can act both ways. It can be an acid or a base. And water is just a classic example of amphoteric, but a lot of other substances can do this as well. And actually HCO3-, which we've looked at a couple times, is an example. It could gain a hydrogen and it could form H2CO3. That would be acting like a base. I'm going to label it B. It could also act like an acid. What do acids do? They give away hydrogen. So it could give one away and form carbonate. So hydrogen carbonate is another example of an amphoteric substance. All right, a couple more practice problems. These are just labeling the conjugate acid and the conjugate base. Let's just do a couple of them. Let's look at this carbonate one, okay? Carbonate is turning into hydrogen carbonate by gaining a hydrogen. We ask ourselves, who gains hydrogens? Bases do. They're the catcher of the hydrogen, okay? And then the base turns into the conjugate acid. Now water is turning into hydroxide by losing a hydrogen. Who loses hydrogens? Who's throwing it? The acid. And the acid turns into the conjugate base, okay? Let's do one more. Let's look at this one down here, okay? HSO4, what's it turning into? HSO4 is turning into SO4 - 2 by losing a hydrogen. Who loses hydrogens? Acids. Acid turns into the conjugate base. And then water is turning into H3O. It's gaining a hydrogen. Who gains hydrogens? Bases do. And the base turns into the conjugate acid, okay? There's one more way that we can ask questions about conjugates. I could say, what is the conjugate base of HF? Okay. I want the conjugate base. Okay. So HF is what I'm starting with, and I want it to turn into a conjugate base. Okay. So if HF is going to turn into something that is the conjugate base, HF needed to act like a what? What turns into conjugate bases? Acids do, okay? So we need HF to act like an acid in order to form a conjugate base. So we ask ourselves, what do acids do? They donate their hydrogens. And so what would be left over after it donated a hydrogen? Fluoride, okay? So that's just a different way that we can ask these questions. Here's another example. What is the conjugate acid of H2PO4-? Okay, so we're starting with H2PO4-. I want it to turn into something that I could call a conjugate acid. Well, what turns into conjugate acids? Bases do. So I need it to act like a base, okay? So I just need to ask myself, if it's acting like a base, what's it going to do? It's going to catch a hydrogen. It's going to take a hydrogen. So it's going to gain an extra hydrogen and form H3PO4. Okay, again, when we're talking about the hydrogen, we're talking about a positive hydrogen. So putting that positive hydrogen together with H2PO4, the positive and negative cancel out and we get a neutral product. One more, what's the conjugate base of HCN? If we want the conjugate base, we need to act like an acid. Acids donate their hydrogen, so that CN minus is what's left over. So that's all. I hope it was helpful. If you have any questions, feel free to come see me.